Today we're doing triangles, but we're doing new triangles. In fact, these triangles are super fancy. They look like this. They're circles. Circles are just really fancy triangles. I'll show you here at the end if you stick with me. First, we have to do a few definitions. The first is a minor arc. Well, let's start with an arc. An arc is a portion of a circle. So in this case, we have arc AB, and we can just label it with this little arc over AB. It's also important to note before we go any further that arcs are measured in the same units you measure an angle, either degrees or radians. So for example, on this arc here, with C being the center, if this angle is, say, 45 degrees, that means this arc is also 45 degrees, right? Because the full circle is 360 degrees. That being said, minor arcs are simply going from A to B here, and they're always less than 180 degrees. Major arcs, however, are going to be greater than 180 degrees. And so in order to denote that we're going the long way around, we need another point. We can't just say we're going from A to B, because then we'll just take the short way. So we have to say we go from A to D to B, and that denotes a major arc. And then finally, we need to, sorry, a little bit too much there. If it's 180 degrees, that's just as a semicircle. It goes halfway across there. Another thing to note, arcs can be adjacent to each other. So we have arc DE and then arc EF. And a further note, we can just add them together. So if I have these arcs AD and I have arc DB, I can just say that arc AB is the sum of those two arcs. Okay, I'm going to go ahead and give you this problem without any further training, see if you can do it. So pause here. I'm back. Okay, so we have a clock here, right? It has 60 minutes all the way around, so 12 5-minute increments. So that means each 5-minute increment is 30 degrees, right? Or 1/12 of 360, and we're going 20 minutes, so that's 120 degrees. You could also think of it as we're moving this minute hand 1/3 of the way around the clock itself. Okay, I'm also going to have you do this problem here. This one's a little more in depth. Again, we'll just pause. And this one has a little bit more going on here. The first part it gives you is that arc EF is 45 degrees. So E to F is 45. We can grab the color here. So E to F is 45. So I'm just going to write, say, 45. Notice here that since we have these straight lines, we have this, that means angle ECF is 45, and we have a vertical pair here. So angle BCA is 45 and arc BA is 45. All these things are 45, right? Since arc BA is 45, it also says that angle ACD is 56. So ACD is 56. So I'll go ahead and do this one as 45. This angle, ACD, is 56. So therefore, DB is just the difference of those two. So it's just 11. All right, moving on. A few more definitions to get through. A chord is just a segment where the endpoints are on the arc or the circle itself. So AB here is a chord, BD is chord, DC is not, because not both both endpoints are not on the circle itself. The central angle are the angles we've seen so far, and they're an angle with this middle vertex at the center C. And then an inscribed angle. So this is the one that we're really going to have to nail down, and we're going to use. An inscribed angle is an angle basically made with two chords that share a point. So this inscribed angle starts somewhere on the circle, and then it goes out in two different directions, and it hits this circle in two other points, and it makes an arc there. So keep that in mind, that inscribed angles go basically all the way across the circle, right? They're made of two chords. Okay, so this brings us to the inscribed angle theorem, and it basically says that when you have an arc AB, so let's pick a value for that. Let's say it's 40 degrees. So, if I had angle ACB, that'd be a 40-degree angle, right? However, instead of going halfway across the circle, we need to go all the way across the circle. So we're going to go all the way over here, and because we're that much, twice as far in this direction, essentially, this angle here is going to be half, right? So that's 20 degrees. Relative to, say, like ACB, again, which would have been 40 degrees. So we'll try this again. If angle D is, say, 10 degrees, that means AB is 20 degrees, right? So an inscribed angle is always half of the intercepted arc that it makes. Okay, here's another problem. Go ahead and see if you can figure this one out. It's pretty tricky, but see if you can put together all the pieces. So pause. Okay, so there's a lot going on here. Again, I'll just show you the answer. But the givens are that angle EDF is 15 degrees. So E to D to F is 15. We can go ahead and label that. Since this angle is 15, I know that EF is going to be 30, right? And that means EBF, right here, this angle is going to be congruent to this angle. They're both 15 degrees, right? Do a little 15 in there. It's not a well drawn one. So I know that this angle is 15 degrees. ABF, well, that one, the arc that it makes, right, the inscribed arc here is given. And I know that that's 44 degrees. So this arc here, or this angle here, is not 44 degrees. This angle is half that, so that's 22 degrees. And so I just have 22 plus 15, which is 37. So give yourself a pat on the back if you're able to get that. Last little bit thing to note here is if we have an inscribed angle that's 90 degrees, then that means that the arc that it makes is 180 degrees. So therefore, it basically cuts the circle in half here. It goes right through the diameter, or it makes the diameter. So just keep that in the back of your mind. It may come up. Okay, so I promised you to show you how circles are the same thing as triangles. I have my, this is in GeoGebra app thing, and it basically has a big circle here. But note that there's a triangle, a right triangle. So if I go over here, I form a 90-degree angle, and I go up. Here's my right triangle. The hypotenuse is 1. See, it goes up to 1. So the hypotenuse is always going to be 1. This angle here, right, is just whatever angle we can adjust. We can change that angle. We can make it bigger and smaller. And we'll see what happens to the sine and the cosine. The cosine is equal to adjacent over hypotenuse. The hypotenuse is 1, so really the cosine of this angle is equal to this x value, right? The change in x. And then the sine of this angle is opposite over hypotenuse, or essentially this y value, right? So the y value is the sine, the x value is the cosine, and then we can just change the angle and see what happens to sine and cosine. If we make it really small, cosine is essentially 1, and the sine is negligible. If we can put it up toward close to 90 degrees here, then the sine is 1 and the cosine is basically 0. And you can see how the sine and cosine go up and down and up and down and up and down basically in each quadrant, right? And they make their values go up and down and up and down. Um, and so circles are intrinsically related to triangles in a lot of ways. In fact, just the formula for the area of a circle, we can show that that's the same as the formula for the area of a triangle. Anyway, we'll see you guys later. Thanks. Have a good one.